Hey, hello everyone. Welcome to today's lecture in the series of solving GATE questions. So, today I will be solving a set of questions from the GATE 2019, question number 35 to 38. As you know, I am solving only the organic questions and I am trying to discuss in great detail, so that just that not we will understand the question, but you understand the whole topic in and around that question. Okay. So, let us start with the first question. So, the question says, the major product formed in the following reaction is. So, you are doing hydroboration basically, followed by hydrolysis in acidic condition. So, these are the choices which are given here and we will go one by one, right. So, B2H6 is diborane. So, the reactive species you know is BH3, which exists as dimer. Now, BH3 is Lewis acid, its octet is not complete and therefore, it accepts lone pair of electron and then basically gives hydride to do the reduction reaction. So, what we understand is it will accept lone pair of electron. So, it reduces only those species which has high amount of electron density. So, generally it is used for reduction of alkenes, because alkenes has a lot of electron density, alkynes, and among carboxylic acids it reduces only carboxylic acid in presence of other functional groups such as esters and even ketones, because they are all electron deficient in nature. Carboxylic acid basically, if you remove proton, it becomes O minus, that is quite electron rich and therefore, that reduces easily. Other thing which reduces is amide, which I will show you after some time. So, basically how it happens is, carboxylic acid, the oxygen lone pair goes and attacks this BH3 and boron gets negative charge, because though it was electron deficient, it was neutral after all. Now, when you form a bond, now 2 electrons were there. So, 1 electron boron has taken, 1 electron oxygen keeps. So, basically oxygen lost 1 electron and oxygen gets positive charge and boron gets negative charge, and then this H minus which will come out, and so that neutrality is gained, and 2 times this attack happens. So, that you get RCOO thrice attached on boron, and then you hydrolyze, it becomes alcohol. So, remember this, carboxylic acid reduces only carboxylic acid and amides among all the carboxylic acid derivatives. So, acids to alcohol and amides, if it is unsubstituted amide or substituted amide, it breaks up here and forms aldehyde. So, it gives you aldehyde. So, this you have to remember, there is no other way. Now, let us focus on a question. So, very clearly now in our question we have our carboxylic acid and we have our ester. So, just now we said ester remains untouched, only carboxylic acid reduces. So, first step will be of course reduction of carboxylic acid to alcohol, and then what happens? And then when alcohol is formed, very simply it will undergo transesterification. Why? Because ester group is there, intramolecular cyclic formation is kinetically and thermodynamically favored. So, now C double bond O will come close to it. So, this will go and attack here and the bond goes up and then it comes down and OCH3 minus lost. So, that will take away basically this proton and you get your lactone ring. So, this is B. Lactone is basically intramolecular or cyclic ester. An important thing is the stereochemistry. See, we did not touch the stereochemistry at all at this center. So, that is retained and therefore, the answer is B. So, it was quite simple question. Moving on to the next question. Now, this was one of the very complicated question. It took me almost so many hours, I do not remember, to solve this. But basically, if you look at this question, what you find out is there is active methylene group. So, you will understand that because base is used, so one of the proton will be taken away and you get a negative charge, and mostly it will go and attack this HCHO, because it has carbonyl carbon which is electrophilic in nature, and then reaction should move ahead. But and you can see that COET remains intact. So, definitely hydrolysis does not happen here. We do not have base also, so hydrolysis will not happen. And another thing is, in all the reaction you see how many carbons are there. Basically, this COET, you will forget about this. You have 1, 2 and 3 carbons plus here 1, 4. But here if you remove this COET part, you still have 7 carbons, right, 7 carbons in all of the substituent. So, definitely at least 2 molecules of this one is reacting and 1 molecule of this is reacting to give the product, and we will go step by step and we will try to understand the mechanism. So, whatever I said I have written here, let us go ahead. So, now this molecule is ethyl acetate. Now, these 2 protons here are acidic, but remember you cannot remove both the protons at one instant. How much ever base you put, how much ever powerful base you put, you cannot remove both the proton. Why? Because if you remove both the proton, the carbon will get 2 minus. Carbon is very small, it cannot stabilize 2 negative charge. So, at one point in time you can remove only one proton and you can go ahead with the reaction. Why is it acidic? Because understand, anything acidic, when that proton is lost, the species, the conjugate base which is formed should be stable, then only this proton will be lost, because it does not mind losing, it is stable. So, that is what happens, you remove this proton, you get negative charge, this negative charge is spread here, it is also spread here. Okay. So, that is how you can find out that this negative charge being spread over 2 carbonyl carbons, and that is how it is stable, right. Let us go ahead. So, first thing will be, you have a base, sodium ethoxide, you should know is a powerful base. It also acts as a nucleophile, but here you see there is no point in attacking this group, because you get the same thing. And so, it acts as a base, it removes proton and you get negative charge here, and that negative charge goes and attacks this aldehyde, this is formaldehyde, and you get this one and you get CH2OH. Now, what happens is, still the reaction is in basic media. Generally OH minus is a bad leaving group, but in basic media it can leave, and that's what happens here. The second pair of base, the second equivalent of base, this will go and take away proton. Why it will take proton? Because this proton is still acidic, because negative charge is stabilized over this carbon and also towards this carbon. So, you get negative charge here, and that negative charge will come down and this OH minus will leave and you get this double bond. Now, this double bond is quite stable, you see, it is stabilized this side also and it is stabilized excuse me, this side also, right, and therefore, this product is formed. And now what happens? Now the second molecule, because we saw that 7 membered ring was formed. So, second equivalent of ethyl acetate is used, and this will take away proton, you get negative charge here. This negative charge you know that it is stabilized over this carbonyl group and this carbonyl of the ester group. Now, this will go and attack. So, you understand this, negative charge on carbon is always more polarizable than negative charge on oxygen. Why? Because carbon is not electronegative, not as electronegative as oxygen. So, it does not hold electron close to itself. Its lobe is very big, its lobe is something like this, this is very big. Okay. So, it is polarizable, it is soft. So, therefore, because it is soft, soft always attacks soft center. Now, attacking this center is soft, whereas attacking this center is hard. Why it is hard? Because here carbon is attached to oxygen and therefore, this lobe is smaller, because oxygen pulls electron towards itself. So, the lobe becomes smaller and therefore, it is hard to polarize and therefore, attacks happens here, it comes here, and where are we? It gets negative charge and this comes and takes a proton from the solvent, thus ethanol here, and then again next pair sodium ethoxide, next equivalent sodium ethoxide comes and attacks here, it comes up and you get a negative charge there, and this one comes down, again the ring formation is happening and you are getting a kinetically favored, kinetically and thermodynamically favored 6 membered ring, and it takes away proton from here. And again in basic conditions, as we know, O minus is a OH minus is good leaving group. So, this proton is still acidic. Why it is acidic? Because negative charge, if you remove this proton, the conjugate base, the negative charge will be stabilized by this ester, and this proton is alpha to OH. So, next step again this proton will be lost again this proton will be lost. Sorry, I thought about this, but yeah, basically this proton is lost because this is also alpha to the carbonyl group, and this comes out and you get here this bond, and then you do hydrolysis and you get this ester, this one leaves rather than this one, and you get beta keto acid, and that beta keto acid, what happens is it undergoes decarboxylation easily. Why? Because, oh sorry, I forgot to draw here C double bond O. So, here there is a C double bond O. So, this comes here little bit you heat, no, if you have carboxylic acid and on beta position you are having C double bond O, then in under heating conditions CO2 is lost, it comes up here and then it undergoes tautomerization and you get the product. So, that is how this product is formed, and the answer is D. It is one of the very tough questions. We have to think about the time also when we write gate questions. Some one or two very awkward question comes. So, it is better not to take risk. Let us proceed. The next question is, you are having this molecule cyclobutane, on that aldehyde group is there. Okay. So, cyclobutaldehyde you can say, and on that you are reacting with Grignard reagent. See, I am saying Grignard reagents, not Grignard, it is Grignard, though we write Grignard because it is based on the name of scientist. The scientist was German, and in German we call it Grignard, and then you are basically putting HCl in it, and you want to know the what is the product form. So, interestingly you can see that in all the product chlorine is attached. So, this was important thing which you have to keep in mind, because generally Cl minus is a weak nucleophile, it does not go and attack. So, if you would have had water along with HCl, then water would have got an attacked and you should have got alcohol. But what I understand is this HCl they would have provided as gas, not normal aqueous HCl, right. Then we will move ahead. So, what are the two things which should catch our attention? First thing what should catch our attention is we are having Grignard reagent CS3 MgBr. So, CS3 MgBr, you know, metal carbon is beside a metal, metal by definition is electropositive in nature, it gets positive charge by giving electron to the neighboring atom. So, it gives electron. So, this is having high, very high negative polarity, and this has quite high positive polarity, and therefore, this is a very powerful nucleophile, very reactive. So, this is the first thing. Second thing what you have to understand is this carbonyl group is there. So, carbonyl, you know, oxygen is having negative polarity because oxygen is electronegative in nature. So, pulls the electron towards itself, and carbon has positive polarity because it has lost electron, and therefore, Grignard reagent will attack here, no doubt about it. Next point what you have to understand is there is a 4-membered ring. So, now 4-membered rings are both kinetically and thermodynamically very unfavorable. So, it will look for an opportunity. So, whenever it will find some way to rearrange, it will break open so that the strain is lost. So, these two things will guide us to the product. This was very simple question, you will see for yourself. So, you are having Grignard reagent, this is the simplest reaction you should know. So, carbon is having negative polarity, magnesium is having positive polarity. So, this negative polarity goes and attacks here, you get negative OMgCl, and then this takes a proton and you get OH, and then this goes and again takes proton, it becomes water. Why we are doing all this? Because we want to make it good leaving group. Now, once water is found, water is a very good leaving group here, because first of all oxygen is having positive charge, very unstable right now, but once it leaves as water, you can see water is everywhere, very stable molecule, and therefore, it becomes wonderful leaving group. And now, the cyclobutane gets the opportunity to rearrange, and therefore, this goes and attacks here, and water leaves, and you get this kind of carbocation intermediate, and then we have Cl minus. So, Cl minus will go and attack here, and see this step, no, this is confusing, we have to look at the product to find out, because I would have thought lot of other things could have happened, because H2O is coming out in the reaction. So, H2O is a more powerful nucleophile than chlorine, and then this H also I could have thought of some kind of elimination reaction will happen, you get a double bond, but Cl minus is attacking here. This is more of a specific reaction they would have seen in some lab. Okay. Moving on to the next question. Now, this was interesting question, not tough, but it's involving question. Okay. So, let me bring it little here. Yeah. So, in the following reaction sequence, the products P and Q are, so you are having iodo arene. So, on phenyl ring you are having iodo group and you are adding lead acetate. So, of course, it is Heck reaction in presence of PPS3. So, triphenyl phosphine will go and interact with it. So, PDPPS3 4 it forms, then OAC twice. Basically, it is Heck reaction. Okay. And Heck reaction is simple, you will get the product quite fast, but this was not very simple. That P, no, especially that last when the elimination happens, because we understand Heck reaction a simple thing, you just remove proton from alkene and add another alkene to it. That's how we know aryl group whatever is there. But here it was not that very easy. So, we will see that part, and the next step was easy, LiLH4. Let us look at the question. Okay. Look at the answer. So, these are the choices. No point in seeing the choice, because this question was quite self-explanatory. As we keep going ahead, we keep getting the product. So, the first step is Heck reaction, but involves little involved mechanism, and before I start this question, I want to solve this Heck so that it becomes clear to everybody. So, this is basically Heck reaction. You have alkene and you have alkyl halide, and you add lead salt to it, basically lead complex. So, this will break up here, lead goes inside, and then this R goes and joins here. So, in a alkene, basically a proton is removed and alkyl halide or aryl halide, whichever is there. So, that goes and replaces the hydrogen and we get this product. This looks very simple, but in this question you can see that it was not very simple. We will find out why. So, how it starts with is basically palladium, we start with something like PDPPS3 4. So, that time 4 ligands are there, it is 18 electron, very stable. So, before the reaction starts, it loses 2 ligand, still it is PD0, but now it is having 14 electrons and therefore, it is reactive. So, what we have got here is PDOAC twice, that was already PDL2 species. Okay, we need not worry. It would have started, we are putting triphenyl phosphine to start the reaction. Okay. And then what happens is alkyl halide is there. This alkyl halide breaks. This alkyl halide breaks and R goes and adds here, X goes and adds here. So, what happens now? PD from 0 it becomes PD plus 2, and from 14 electrons it becomes 16 electron center. So, it is called as oxidative addition, because from 0 oxidation state has increased to 2 and addition has happened, one X and one R has been added. Fine. And then what happens now? This alkene gets added to this Rx. Now, this alkene addition is what most of people do not understand. They will understand all the mechanism, but this alkene addition is little bit confusing. So, we should know. Now, what happens, this alkene, this R prime you have to define. If you have something like electron withdrawing group. So, what happens? Electron withdrawing group means this pulls electron here. So, you get positive polarity on this carbon, and you can think as negative polarity, not exactly, but definitely positive polarity comes on this one. So, you can write here as positive polarity this and negative polarity on this, and now we have already formed this one, you remember Rx has reacted with the PDL2 and this is what you have got. Now, palladium has positive polarity because it is metal, metal by definition electropositive in nature, and then the R has negative polarity. So, this R minus will go and attack where? Here, right, and this comes up and goes and attacks this palladium, and therefore, remember positive polarity is on the terminal because electron withdrawing group was there, and that is how it happens. This negative polarity was not there in the beginning, but once R minus attacks here, this carbon gets electron, therefore, we had written here negative polarity, and that negative polarity goes and attacks the palladium, right. And then we move ahead. When you have electron withdrawing group, sorry, did I not talk about electron pumping group? I have not talked, so maybe basically I am telling about that. Yeah, So when electron withdrawing group is there, this R minus goes and attacks here, and this you get. This is what just now we talked about. But when you have electron pumping group or electron donating group, then what happens? See, it pumps electron here, pushes electron towards this side. So this one gets negative polarity and this one gets positive polarity. So because it is having positive polarity, the R minus will go and attack here, and this comes here, and this will attack the palladium. So this is what guides the Heck reaction, and this is where most of the mistakes happen in competitive examination, because we are not very sure where to attach R and where to attach the palladium. After that only elimination takes place. Fine. And then what happens? And then what happens? After this is added, no wait, sorry, what I am trying to say is this, when you are adding on the alkene, okay, when you are adding on the electron center, so something like this is pumping group, so it will come here. It doesn't matter if it is withdrawing group, then what happens is here you get positive polarity and here you get negative polarity. So this R minus will attack here and this will go and attack palladium here. So that we have already talked. What I am trying to say here is the addition of R and the addition of palladium is very, very stereo selective, and always happens in syn addition. It will happen from the same phase. So imagine this H, they are on the board, and this H is also on the board, and this R is also on the board. So on the screen you can see here. So R minus attacks here from the front, PD also attacks from the front. So I am putting both of them towards the viewer. This is very important step. Okay, you can distinguish between good organic chemistry and a simple organic chemistry is good organic chemistry will always understand stereochemistry better than normal people. And then what happens? Now this palladium has to leave to get back the alkene. Now this R will not, carbon-carbon bond will not break, and therefore the rotation happens so that hydrogen and this palladium comes syn to each other, and then elimination happens. Okay. So basically this is what happens. So this we got R and PD, and then you rotate it, hydrogen comes front and this goes and attacks here and comes back. So let me just revise for you once again this cycle is very important. So basically you start with PDL4 0, it becomes PDL2, Rx you attach, you get R and X, and then R will attack on one carbon, PD will attack on one carbon. It will happen by syn fashion. So that's what I have shown here. But then elimination has to happen. So this carbon has to rotate, this bond has to rotate, so that one of the hydrogen has to come in syn fashion with this palladium, so that this leaves and you get back alkene, and you have added one extra R to it. Okay, that's what is Heck reaction, and this step is called as carbopalladation, where you are adding this. Okay, let's move on for our question. So now this question is very clear. So this is not alkyl halide but aryl halide. You are adding PDOC twice. So very simply this will break, PD will get added here, and iodo also will get added on the palladium. So that is no issue with it. Now what is important is now reaction has to happen on alkene. Okay, now the reaction has to happen on alkene. So we will rotate it so that alkene comes on top, so that we can think about the reaction. Basically we saw just now what has happened, what happened. So on alkene is there, on alkene on one side palladium will attack, and one side R will attack. So this is the R. So R, you know, R is having negative polarity. Why? Because it is attached to a metal by definition electropositive in nature, so it has positive polarity. It gives electron, gets positive polarity. Now where will this carbon attack and where will this palladium attack? You understand, though Cn is electron withdrawing group, but this is carbon CH2, so it will undergo kind of hyperconjugation, and therefore it acts as a electron donating group. It's a alkyl group. So when it pumps electron, so what happens? On this side you get negative polarity, so that palladium attack here, and this one gets positive polarity. So very clearly this will go and attack here, and this will go and attack on the palladium, right. This was the important, this was the complex reaction. So, this negative polarity will go and attack on this carbon and this will go and attack on the palladium and you get this. And very important, it happens by syn fashion. Though I drew it thick, I should have not drawn thick. Why? Because this carbon sp2 hybridized, so this has to be planar. But why I do thick? Because I want you to understand, that it is happening by syn fashion. So, if it is coming from front, this is also coming from front. But actually I should have drawn this as plane and this also as plane and should have explained stereochemistry some other way. But if I do not explain stereochemistry also is fine, because we will see very important, because there is no rotation possible. So, whatever has to happen will happen in this conformation itself, but you have to understand it happens in syn fashion. Now, PDOC will be lost. So, what we see is when alkyl group is attached, alkene is there, that rotates and then proton comes in front of PDOC twice. But now on this carbon you can see this is carbon, this is carbon, this is carbon, there is no hydrogen. So, nothing can rotate, it cannot rotate also because it is cyclic. So, this is what it is bit different from normal Heck reaction, elimination is happening from the other carbon. So, now this carbon has two hydrogen, one will be towards the viewer and one will be away from the viewer. So, whichever hydrogen is in the same plane with PDOC twice, that will undergo elimination, So, Ag2CO3 is a very mild base, but it is a mild base. So, this will go and attack proton and this comes up here and this leaves and you get a alkene. So, this was very interesting question, it took some time for me to solve. So, this was important. And then what happens? And then you are using LiLH4. LiLH4 powerful reducing agent, reduces Cn to CH2NH2. TS minus is not a good leaving group, OTS is good leaving because it is stabilized. So, it does not even touch here. And then what happens? And then in the next step, if you see, they are adding acetic anhydride. So, this is the acetic anhydride. So, of course, this carbon is electrophilic in nature. So, this nitrogen lone pair goes and attacks here, this goes up and you are getting amide formation. So, this is your product, that is Q. So, the answer is C. Okay. That is it for today. This was very important question. Please revise it again, go back and do that. Thank you very much.